Okay, Assalamualaikum and a good morning. Welcome back. So today we will continue with our lectures. So let me just share my screen. Okay, so let us just recall what we did last lecture. So again, oh, by the way, I've already uploaded lectures 6 and 7 in Putra so you can now have a look at it. And lecture 8 I'm still typing, and for today, of course, I've not typed the notes as yet. So today we probably will do the lectures on the whiteboard again. So let me close this. So let us recall what we did. So essentially that gone into the chapter of Canonical Ensemble. So let's recall that. It's a Canonical Ensemble. So one considers, for example, a system of interest interacting with a heat bar. Okay. And we have actually looked at various different formulas. One of the formulas is essentially the number of different configurations, configurations with some energy, for example. You remember that your system is essentially exchanging energy with the heat bulb, but the system itself will have certain energy levels. So let me just write it down first. Number of configurations with energy EI for the system. So this is given by WEI, and we have essentially made the connection with the heat bath by saying that this number of configurations is just simply the number of configurations of the total internal energy minus the energy level of the system. So that essentially when it add up, when this energy adds up with EI, will just give you the total energy. Okay, so this is from the previous discussion, and what happens in this particular case, the heat bath give the temperature dependence onto your number of configurations. Okay, so let me just write that down. Let me just check with the plus and minus sign. Certainty. So that will be just UT over KBT times with the sum of all possible different levels for your energy levels for your system. Okay. And essentially what that gives us, I think there's something wrong there. Let me just check. Yeah, I'm missing something. So I should be having this as well. and then multiply with the sum. So you can look at the previous lectures that we had. So so once you have this number of possible configurations for each energy level, then one can actually give you the essentially is the statistical probability, which is given by, I have to write slowly, otherwise this thing will just lag behind. Divide by the sum EJ just okay, I should be getting rid of that sum. So let me do just that. Sorry, I've just forgotten what I've done. So that's just that, and then this will give you E minus EI KBT, and then sum J E minus EJ KBT, and the denominator we have a symbol for it, which we introduced the last lecture, which is called Z, and this Z is called the partition function. So before we go and proceed to do calculations on this canonical ensemble, let me just say the following. So if we look at the probability over here, you can see that the dependence of the temperature, you can see is coming from this exponent with the denominator here. Okay, so at low temperatures, what's going to happen? I didn't quite see this, I think, in the last lecture. Low temperatures, so in other words, this is almost like, no, this is a very small number, and contributions from larger energies, okay, when you divide something with a small number, this will get large, okay, and then E minus a large number is going to be small. So in other words, at low temperatures, then what's the low energy states are more probable. That's all I want to say. Are more probable, particularly the ground state, for example. And then as temperature increases, so in other words, maybe I should say this because we talk about occupation of the states. Okay, so that will tell us should I do this? Need the right word for this. States that are mostly occupied are the lower energy states. Okay, so so as you increase your temperature, as temperature increase, more high energy states gets occupied. Okay. Until you allow the temperature goes to infinity, a very large number, then all states are essentially equally probable. Okay. So these are essentially some physical idea that you have to have this Boltzmann probability distribution. So I think that was something that I missed out in the last lecture. So today we're going to go into the new section on entropy. In Canonical Ensemble. So what we're going to do, we're going to slightly modify the thing that we have seen before. So in the case before, we had this system of interest, say, okay, so system of interest, let's call this system M. Okay. And so let me just push this in so I can write better. So, and previously we just have the heat buff. The heat buff are usually an enormous system that sort of if you think of it, it's like having a system with a infinite heat capacity. So, but now instead what we do is to replace the heat buff, okay. So this now interacts with a replica of the systems, and minus, I should say, distinguishable. That's going to make some sense. Distinguishable replica system. That means you can identify which system is M, which system is M-1 or M-2, and so on and so forth. Okay, replica systems. So there would be, for example, over here, let's say we have, let's suppose now so this, okay, let me just write this. Systems, and then this whole thing sort of replace the heat buff. Okay. So let us now consider the number of systems. Let the number of systems in some quantum state psi I to be equals to Ni for some I or given set, okay, where you need to have this sum over Ni I has to be equals to N, the total. Can you actually see the cursor? Anyone? Somebody? Are you seeing the cursor? Okay, great. So meaning there will be, together with this m minus 1 replica system with this one system of interest, there will be m altogether. Okay, the total number of identical systems. Right. So now what one can do is to count, okay, the number of ways arranging, say, n1 systems, okay, with energy or with quantum state with state psi 1 and 2 systems with state psi 2 and so on. Okay, so how do you count them? This is just combinatorics that we have actually learned before this. So this will be given by this number of configurations here is given by W. So the total number of systems is going to be total number of ways. If you consider all possible ways to describe the system, there's only going to be m factorial, but within this m factorial thing, there will be n1 systems with certain state and so on and so forth. So you have to divide by those. So that gives you n1 factorial, n2 factorial, n3 factorial, and so on and so forth. Okay, so that will be the number of ways of having this so-called subsystem within a particular state. Okay, so what we're going to do next is to consider when these numbers are going to be large. Consider very large m and i's. Okay, so when you consider them to be very large, then you can use your Stirling approximation. Okay, so use Stirling approximation. And that should give you, say, the formula of entropy for system M to be given by KB log W, which is going to be now written in terms of no, given this particular formula, this will be given in terms of this. Not sure I write this. Okay, m log m minus, okay, because the minus sign is coming from the denominator, so you get sum I ni log of ni. So that is just direct application of this W inside this log. We're going to do, maybe I should not write that now. Let's move that forward. Okay. So what's next is over here, what you're going to see, you have this sum ni here. So, and you have this capital M over here. So in order for me, for these two terms to look rather similar, what I'm going to use is the following. Use M log M. And remember that from above, oops, not that, down, you have this sum. Okay, so I can use that now. Oops, get confused now. M log m will be the sum of ni log m. Okay, so I can now substitute this over here, and I will be then I will do something else. Okay, let me just write it down first. Sm. So I would have this. Okay, let me just write this in full. So let me just write this thing down first. So this becomes sum ni log m minus sum ni log ni, and what I can try to do is to make them having the same negative sign. So what I'll do this is to rewrite this as follows. So I need to do something over here. Yeah, okay, let me just, so I will write this thing down first. You can see what I'm doing. After that, I'm going to take the inverse of that. Okay, so the log of inverse of that is actually the minus sign. So I'm going to cancel that minus signs with a minus sign there. So I have that. Okay, that's halfway through. So, and then I will bring out a factor of m out. So that gives me minus from both terms kbm. So I will have now how should I do this? M summed. Okay, maybe I'll just write it down first, then you can see the logic of it. So ni over m log of ni over m. Okay. Now this m over here simply cancels out this m in front. Okay, and the other two is coming from the sum of these two. So this is log of 1 over m, and then this is log ni, so that adds up, the addition of the log becomes the multiplication, so to speak. So you have ni times 1 over m, which gives you that. Okay, so that is essentially what we have. And now we can start doing the approximation there. As m goes to infinity, or very large, then your ni over m will be approach what we call the statistical probability. So this gives you the problem, not the problem, probability. I can read my own notes. Probability of finding system in state psi. Okay, so that now allows us to write the following. So one can now write entropy per system. Remember that we are consider m identical systems. Okay? So for each system then is given as follows. The entropy of per system is given by Sm previously, okay, divided by m. So that will cancel off with this capital M. And that gives you this relationship minus Kb sum over Pi log Pi. Okay? And this is sometimes called the average entropy. Of system in canonical ensemble. Okay, so in other words, we have almost some similar thing that we have actually probably have seen before, but not quite in this way. But now let all probabilities be equal. So that means that S, bring this up, that S is going to be given by minus KB, and if all these things are going to be the same, so it's going to have this equal probabilities of 1 over W. Okay, so this is sum I, where all Pi is just given by 1 over W. And when you sum over all I, that gives you essentially your W, and that reduces to KB log W, which is essentially your Boltzmann formula that we have seen before. So in other words, it's encouraging that in this particular limit where you have equal probabilities, you get back to what Boltzmann started out with. But remember that this is derived from consideration of quantum states, but with classical probability. That means equal probability. Okay. So in other words, even though they look the same, but it has a different underlying reasoning from the one given by Boltzmann. Okay. Okay. So that sort of finished one section. So the next one is to consider about the partition function. So let me just move this thing up. So, so let me just write down that section on book. I may rename this later on when I get more better ideas of how to make this continuous in terms of ideas. Bridge to thermodynamics through Z. Okay, now recall that your so-called partition function. Okay, recall partition function before we understand it in a particular way. Partition function Z plays the role of normalization. Such that sum PI must be equals to 1. So that is essentially just, it plays more of a, what you call, so it's more mathematical rather than anything else. But your partition function could be related to something physical, which we'll do in a minute. Okay, so partition function can acquire a physical role in a way, and this will relate to thermodynamic properties. So this is what we're going to do. Okay. So let's recall the case of the canonical ensemble. Okay. Where you had your probabilities given by this. Let me just write that P doesn't look very nice. Pi equals to E minus EI on KBT divided by Z. And then we have also done entropy for this, which is now given by S minus KB sum Pi log Pi. Now what one can do now is to write your log Pi. So write, because Pi is given by that, right? So write log Pi equals to, so the log of that is just minus EI on KBT, and then log of 1 over Z is just minus log of Z. Okay. So next you substitute this in S, entropy, and then you can rewrite your S as KB sum over I Pi EI over KBT plus log of Z. Okay. Now what happens here, there are two parts of this sum. Okay. So there's a log Z part, but the other part which has this Pi EI, so that is essentially, okay, the probability of the state in psi I, which is the state of energy EI. So in other words, what one can relate this is with the idea of an average energy. Just look my notes. Relate to average energy. Which is given by U bar, which is taken from Pi, the probability of energy EI, times with the energy itself, and that gives you the average energy. So there you can see that this will comes in here, and essentially that will give you the following expression for entropy to be equals to U bar T over T plus KB log Z. Okay, but now I can sort of bring the T on the other side, so I get T times S, and then bring that T times S to the other side of the equation, and arranging those, we are now able to write the following: U bar minus TS equals to minus KB log Z. But what is this? This is essentially your free energy, Helmholtz free energy. I'm losing a T somewhere. Hang on. U bar T. So I'm multiplying T over here, so I'm multiplying T throughout, so I should be having T here. Sorry about that. So I will have KBT log Z. So in other words, we have now written your free energy in terms of partition function. Okay. Free energy in terms of partition function, or one can think of the other way around as well. Your partition function is related to your free energy. And remember that free energy over here is a thermodynamical variable, and so your partition function on the other hand, so let me just write that down so that you get the idea. Partition function comes from the microstates, and then it's related to this thermodynamical quantity. Okay, so now you can see that okay, there is this physical idea of this partition function being related to this free energy, the Helmholtz free energy. Okay, so that gives you a kind of a new understanding of what your partition function is. Okay, what else? Okay, I think I can skip some of the arguments here. I'll put it down in the notes later on, sorry. So next thing is to look at thermal equilibrium. Conditions for thermal equilibrium. Okay, so earlier we had the Boltzmann probability distribution. So this is given by PI. This is PEI, which is equals to E minus EI on KBT divided by Z. And one can think of this as a constraint. Okay, so can act like a constraint where recall that this is actually so I should put this down then, pi equals to u. So in other words, having this form relate with this constraint, so in other words, this thing is itself just like a constraint. So one can say now that, okay, if one does not have Boltzmann probability distribution, then system is not in equilibrium. So in other words, to have the system in equilibrium, one needs this Boltzmann probability distribution. Let's now make this a little bit more quantitative in some sense. How do you actually see when things are in equilibrium or not? So let's consider the case system with energy eigenstates maybe I should be more precise here. That means I have particles inside here, a system of n particles with each of these particles in a particular energy eigenstate. Then we also need some reference energy level with reference energy level given by the ground state. Okay. And we write the ground state for simplicity to be equal to 0. Okay. So then we can now think of comparing the probabilities for each particular state. So in other words, I can think of Pi now as the probability of energy state Ei, but now I'm going to take the relative probabilities to the ground state. So this is P naught. Okay, so what's going to happen is that, okay, when you do that, this part has this denominator to be common on both Pi and P naught. Okay, and that will get cancelled out, and we just have this negative exponential thing. So this must be true for all I, must be true for all I, so that it behaves like, so you get essentially the Boltzmann distribution. Now, essentially, again, when you have things in equilibrium, okay, remember that all the subsystems, in this case all the system with a particular energy level, should have the same energy as should have the same temperature. So one can check this. Okay. Check the temperature. All subsystems have same T. And how do you get this T? Is by inverting this particular relative probability. Okay, so I can now rewrite your T using that formula as follows. T equals to minus EI, and then this one I can rewrite in terms of the K, what you call earlier probability expression, which is, oops, that, sorry about that, I'll keep forgetting about this. Oh dear. Where was it? Have the probability in terms of the log. Yeah. So here is essentially the formula, the entropy would come in somehow. Let me just go down. I would just write down the expression so that you can actually see where it's related. So this will be equals to KB log. Oh, actually, that you don't have that. You don't need entropy in that. Well, you can relate with entropy if you want to, but in this case, you just invert this particular formula. This is exponential, so the inverse mat of your exponential is the natural log. So this will give you log of pi over p naught. So one could now check if the system is in the right equilibrium state by calculating the temperature. So in the book, see example in the book. So I will not go into it. It's pretty simple. To see, you have these different energy states with different probabilities. Could you actually tell whether this system is actually in equilibrium? Then you can check the temperature. So all the energy levels over here with the probabilities over here should give you the same temperature. So I'm not going to do that. The next thing, should I finish this off? I have just one more section. Probably okay. In this, maybe I should do that in the next lecture. So what I want to do next is probably just discuss with you about, okay, there are two things, two matters to discuss, which I hope you can discuss it on the WhatsApp group. One is the replacement lecture, the 1 hour that we missed when I had this conference going on, and then so this is 1 hour, and then the other thing is sometime tomorrow, I suppose, there should be a student-centered learning module. Okay. this will be done in groups of 4. So you can take your assignment partner and then find another pair of partners to form these groups of 4. Okay? So these are mostly what you call reviewing some papers that relate to topics in this particular course. Relates to topics, of course. Okay, so I want you to discuss among yourself regarding this, and then probably come back to me by when's the next lecture will be Thursday. By Thursday, can you do that? Or am I talking alone? You do that?
Boleh, Doktor.
Okay, you discuss this among yourself. So for the LCL, you can try to find your groups of interest, and then for the replacement lecture, so that I don't need to be reminded by the head of department to replace any any lectures being missed. Okay, so I will now take your attendance. And that should be it. So I think that's all for today. So thank you, everyone. Okay.
Thank you, Doctor.
Thank you,
Okay.
Doktor.
Okay. Bye.
Thank you, Doktor.
Bye, Doctor.
Thank you, Doktor.